Welcome back to trigonometry. Today we're going to be looking at parametric equations. Okay. Sounds different and new if you haven't seen this before, but we're actually going to be building on stuff we already know about. We've already been working with various kinds of functions, like the y equals f of x sort of functions, where you had, x, y ordered pairs. We've also dealt with like the r equals g of theta functions when we talked about polar coordinates, and that's where you had the r and theta coordinates there. Now another way to deal with functions is to have a pair of functions evaluated at t. X equals f at t and y equals g at t. And each of these functions evaluated at t ends up giving you your x and y. T is some real number in an interval I. And this is where we're going to get into parametric equations. Parametric equations, you've got what almost looks like three variables. You've got the one t variable, which might, in physics, some physics problems might be time. And then you evaluate the function at time, and you might get one coordinate versus function at time, you might get another coordinate. Like throwing a ball, for instance. You throw your ball, if it travels in a parabolic arc, you've got a horizontal distance x, and you've also got a vertical distance y that this thing is traveling. But in addition to that, you have a time variable. So you can look at its horizontal distance it's traveling as a function of time, t. And that's the x equals f of t. You could also look at its height it reaches as a function of time. And that'd be like your g of t, y equals g of t. But then the two together, the x and y, describe the pattern or the shape of the arc that the ball follows as it flies. So you've got another way to help you to start analyzing these functions. And that's what parametric equations help you to do. So you have a plane curve is a set of points x, y such that x equals f of t, y equals g of t, and fg are found in the interval I. So the x equals f of t and y equals g of t are parametric equations with parameter t. So these two are parametric equations. And the parameter is t. So like throwing the ball, the parameter would be in terms of time. So within that parameter, time parameter, what's going on with x and y. Okay, so that's where we're going. That's what we're going in this lesson. Now what I want to do is just dive into working with some parametric equations and seeing what kinds of things you have to be able to do with them, and then looking at some actual word problems dealing with parametric equations. Okay, let's let x equal t minus 2 and let's let y equal t squared minus 1. And this is for t defined with the parameters being in the interval, closed interval from -3 to 3. That's the parameters right there. And let's say we want to graph a set of ordered pairs x, y. Okay. what we can do is just make a table. We're going to make a table with t, x, and y, and that'll give us some ordered pairs x, y that we can plot on the grid and then see what kind of shape we get. Now since it's for t in -3 to 3, let's just pick some values of t starting with -3 and going up to 3. I'll pick integer values, but keep in mind the t values can be in between those two. It can be fractions and stuff. But if I just pick some integers, that'll be enough to get some points and get an idea of the shape of the graph. Alright, x is t minus 2. So if we take each t value and subtract 2, we'll get x values. Y is t squared minus 1. So if we take each t value and square it and then subtract 1, we'll get the y values. Okay. And that should be enough to try to graph on a grid here. Alright, first xy ordered pair we've got is -5, 8. Okay, so -5, 1, 2, 3, 4, 5, and then go up 8. 1, 2, 3, 4, 5, 6, 7, 8. So we'll get right here. Then the next xy ordered pair was -4, 3. So 1, 2, 3, 4, up 1, 2, 3. The next pair was -3, 0. Next one was -2, -1. Next one was -1, 0. Next one was 0, 3. And then 1, 8. Now we've all have some kind of a college algebra or algebra level background. So in looking at these ordered pairs, you could probably get an idea about what kind of shape's going to come out of this. If you want to, you can get some more ordered pairs. You could find some other t values between these integers and find xy ordered pairs, and that would maybe help you fill it in more. But you don't need to go below -3 or above +3 because that's your parameters we've set. But you should be able to recognize that this is a parabola with a vertex at -2, -1. It's got a maximum value at -3. The maximum value is 8. It's got another maximum value at 1. That's also a maximum value of 8. And forgive my drawing. It's really hard for me to draw nice and smoothly on this tablet here. But there you go. It's a parabola. Now the really fun thing is that you can also take these parametric equations and you can put them into rectangular form. You can find the rectangular equations and that'll just confirm what you got here in the graph. Let's take x equals t minus 2. And let's take y equals x plus 2 squared minus 1. And t is over -3 to 3. Well, if t is over -3 to 3, x equals t minus 2. So x, let's see here, -3 minus 2 is going to be -5. +3 minus 2 is going to be 1. So it looks like the domain has to be from -5 to 1. And then if you plug in -5, plug in 1, you'll be able to see what your y's would be. If you want to go ahead and put this all into rectangular form, that means you won't have any t's. I was reading the wrong thing. I already have brought down the t for that's rectangular. Sorry about that. Hopefully I didn't confuse you too badly. Probably wondering where that came from. You'll see in just a second. Alright. This is a t squared. Woo. -1. That's the original equation. Alright. So then, in order to put this completely into rectangular form, what you do is you take the equation that's the easiest to solve for t. And I think that would be this equation, because it doesn't have any squares or anything in it, unlike this y equation. So let's go ahead and solve for t by adding 2 to both sides. And then you could take whatever you get for t and plug it into the other equation. And that's how I got the equation you saw a minute ago. And now t is gone, so now you've got the equation in rectangular form. And if you look at it closely, it fits the parabola form. F of x equals a times x minus h squared plus k. Do you guys remember that? That's for a parabola. In this case, our parabola is going to hold water. It's concave up. Then the vertex is supposed to be at -2, -1. If you come up here and look at our parabola, it has a vertex at -2, -1 right here. And it's concave up. It holds water. So whether you have it in parametric form or in rectangular form, you end up with the same graph. Alright, let's look at another one of those. It's not going to be a parabola, but let's look at another one where we have to convert and then work with that. X equals 4 cosine t, y equals 2 sine t, and we're told that t is in 0 to 2 pi. Closed interval 0 to 2 pi. Okay, so when you're taking cosines and sines, if the interval is 0 to 2 pi, that tells you a little bit about that. That means x can fall anywhere from -4 to 4. And that means y can fall anywhere from -2 to 2. Because you take 0 and 2 pi and start looking at what's happening to the cosine, it ranges from -1 to 1, and then times 4, so it's going to range from -4 to 4. And then sine from 0 to 2 pi is going to go from -1 to 1, times 2 is going to go from -2 to 2. Okay, so I did that out of the way. What can we do with this to try to get rid of the t? Well, there's nothing that springs to mind that we can do with each one individually. But I notice one has a cosine and the other has a sine. So if I could somehow get this in a form with like a sine squared plus cosine squared, that would be beautiful. Because sine squared plus cosine squared is 1. So let me do this first. Let me divide both sides of this one by 4, just to get cosine t by itself. And let me divide both of those sides of that one by 2 to get sine t by itself. Well, then if I square both sides and add these together, I can get an interesting result. I got x squared over 16, and I'll add that to the y squared over 4 equals, and I'll have cosine squared t, and I'll add that to sine squared t. There's my cosine squared plus sine squared, which is just 1. And now the equation is in rectangular form. Okay. Now to get the graph, I could do a big table of values and see what happens. Like if I plug in -4 for x, I'm going to get that y is 0. If I plug in +4 for x, I'm also going to get that y is 0. If I plug in -2 for y, I'm going to get that x is 0. And if I plug in +2 for y, I'm going to get that x is 0. So I just got those using the ends of my x and y intervals. But you can take values in between and start plugging them into the equation and see what happens. And when you do, you're going to find that you get an ellipse. And you don't even have to know what an ellipse is. Just if you start, getting enough points, you'll start to see this shape, and then you can connect the dots and and get the shape. Like that. Pretty cool, right? Now, or in the future, or if you've already taken pre-calculus, you've seen these before, or if you're going to take pre-calculus, you will see these, or something. But the ellipse, if you have this form, if you have like x squared over a number plus y squared over a number equals 1, like this, you have an ellipse. The square root of the number below x squared tells you how far right, how far left you're going on the x-axis. So the square root of 16 is 4, so we went 4 here and negative 4 there. And the square root of 4 is 2, so we went 2 up and negative 2 down there. And that's the ellipse centered on the origin. You have this equals 1. But again, you don't have to necessarily know everything about ellipses. You could just do a table of values and you would get this shape come out of it. Now another thing you can do is put it in the calculator. Just like the calculator will do rectangular and polar, it'll also do parametric. Go to your mode, and down here underneath radian and degree you have function, parametric, polar, sequential. Go down and select PAR for parametric. And when you do that, you now go to the y equals screen, and you have x sub 1 with t and y sub 1 with t. So let's type in 4 cosine and then hit the x key and it'll automatically give you a t. And then let's type in 2 sine with the t. And then let's go to the window. T min is 0. T max needs to be 2 pi. T step, maybe we'll do pi over 2. X min is going to be negative 4. X max is going to be 4. We'll do increments of 1. Y min is going to be just negative 2. Y max is going to be 2. We'll do increments of 1. Let's see here. So graph. Okay, that's not looking quite right. I didn't quite put something in right. 4 cosine t, 2 sine t, and let's make sure that, oh, go back, let's put our mode in radians. It is, okay. We're in parametric. Dot in my window. And then 0. T max is 2 pi. Wonder if my t step might be too much. Let's see here. Let's try 0.05. See what happens. And then my x min was negative 4. Yeah, my t step was too much. It wasn't getting around enough shape. Negative 4 to 4, scale 1. Alright, so let's go back up to t step. What if I do 0.025? See what that does. Yeah, that's probably as good as it's going to get. If you're too drastic with your t step, then it's going to have fewer points and connect with straight edges instead of being rounder. It's just the way the calculator works with that. But there you go. There's your ellipse. The x value is going from negative 4 to 4. Y value is going from negative 2 to 2. So it is important when you're doing parametric graphing to make sure you go to your window and set it appropriately. Because you got to make sure you have the right parameters in there. Okay. Let's see, what else might you be asked to do? Well, you might be asked to take a rectangular equation and put it into parametric form. And when you have to do that, there can be multiple correct answers. Like, there's 2 that spring to mind for me here. One is that you let x equal t as one of your parametric equations. And if you do that, then y equals t minus 3 squared minus 1. And since x can be any real number, so can t, so t is, the parameter for t is negative infinity to infinity. That's one option. It's not the only option. Another option might be to let t equal the x minus 3 in the parentheses there. So then x equals t plus 3. And if you're going from rectangular to parametric, you're trying to get an x equals and a y equals. And if x equals t plus 3, or t is x minus 3, then you can take y and say t squared minus 1. And still t's parameters are negative infinity to infinity. There's no limitation set at the beginning, so t's not going to have any limitations there. Okay, so that's got two possibilities. That's not the only two, but so if they're asking you to take it from rectangular to parametric, you're going to find there can be multiple answers. If it's a multiple choice situation, find the choice that works. It's just going to be, if there's 4 choices, one of them will work, 3 won't. So. Alright, now let's get into some more application stuff dealing with this. One of the application deals is looking at something called a cycloid. It's a case of a trochoid basically, if you have a circle, you have a point on the circumference of the circle, as the circle rolls, the cycloid is the shape that's traced out by a point, the path traced as the circle rolls along a straight line. So as circle rolls straight, point travels on cycloid path. Now cycloid is defined parametrically this way. You got x equal to at minus a sine t, and you got y equal to a minus a cosine t. And t could be in negative infinity to infinity. So you just keep on going as long as you want. Okay, but you might be asked to graph a cycloid. So you might be given something like x equals 2t minus 2 sine t. Okay, so this first equation, a is 2. And then y equals 2 minus 2 cosine t. So in that equation, a is 2. And in this case, t is going to be in 0 to 2 pi. So we don't have to go any further than 2 pi. Now up here, t is negative infinity to infinity. It can be in there. We're going to define it specifically as 0 to 2 pi. Okay, the cycloid's very round. So what we're going to do is we're going to get some values from 0 to 2 pi and get an idea about it, but we know that it's very round. So once we get a few points, we can just connect the dots, round it out, and there's our curve. Okay, so let's make a chart. Let's say a t, x, y kind of chart. Alright, we said over 0 to 2 pi, so let's start with 0. And let's do pi over 4. Let's do pi over 2. Let's do 3 pi over 4. Let's do pi. Let's do 5 pi over 4. Let's do 3 pi over 2. Let's do 7 pi over 4. And let's do 2 pi. All right, we're going to take those values for t, and we're going to plug each one into the equations. So, like for x, you plug each t value in for t here and see what the x value is. And then for y, find cosine t and plug it in here, and then find each y value. Well, I went ahead and did this. So when I plugged in each value for x, I went ahead and did this and got some decimals. I just took the decimals to 2 places because I figured that's sufficient for trying to plot these on the graph. We don't really need more than that, I don't think. Now, I did not double check, so hopefully I didn't goof anywhere. Of course, if I goofed, I wouldn't have you to shot at me right now, but you could always email me if you ever see something in a podcast that doesn't look right. You always email me and let me know. Yeah, assuming it's not something I immediately corrected or whatever, but let's see here. Alright, so let's take those values and let's plot them on our grid here. So we got 0, 0. I'm just going to assume each line on the grid is 1. So we got 0, 0. So xy coordinates, we got 0.16, comma 0.59. We got 2.14, comma 2. We got 3.3. I goofed already. Sorry about that. Erase. I didn't go all the way over to 2. 2.14, 2.14, comma 2. It should be right there. We got 3.3, comma 3.41. I'm going to have to scroll up here. 3.3, comma 3.41. So about right there or so. That's one of the problems with trying to kind of guesstimate here. The 2 pi or 6.2 or so, comma 4. Then 9.3, comma 3.41. And then 11.4, comma 2. And 12.4, comma 0.59. And then 4 pi is around 3.14. That's not too far off from 12.4 either, but we get 0 right there. Alright, this one looks off, so let me pull up my calculator real quickly. Let's see here. I don't think it's the y value that's off. I think it's the x value. Because that one I was plugging in 3 pi over 4. Let me see what that x value should be again. Let's see. Alright, 3 second function pi divided by 4. And then that's the t, and we're timesing by 2. And then we're subtracting 2 times sine of 3 pi over 4. You get around 3.3. Yeah, it's around 3.3, so I guess just the way I'm Oh, that one was fine. So which one was it? Oh, the pi over 2 one. The pi over this one right here. That's the pi over 2 one. That's the one that's not looking quite right. All right. Pi over 2 times 2 will be pi. And then we're subtracting 2 sine. And of course, you could be using your, if you really want to use your unit circle, you can, but I'm using the calculator just because we have to put in all these other pi's and stuff. You get 1.14. For some reason I had 2.14 written down, so that's the one that's messed up. That's why it's not looking quite right. Okay, so let's erase this one, and let's erase this. And let's go ahead and put in 1.14. Alright, that's going to look better. We're going to have 1.14 comma 2. So 1.14. See, where I had the dot the first time was the correct place. I just had the wrong number written down on the chart. Alright, well, close enough. That looks so much better because the cycloid's going to be very round. Let's connect the dots, make this nice round shape, and there's your cycloid. You now have it graphed. Woohoo! Nice, right? Okay. So that's, again, an example of why it's important to know what the graph's supposed to look like. So that way you can catch anything that looks off. Even though you have your calculators, sometimes the calculators don't fully make the graph, so it's good to be able to recognize what it should look like and try to troubleshoot why it doesn't look the way it's supposed to, if that happens. Okay. Another application. Parametric equations are used to simulate motion. Let's say we throw a ball. Velocity is v feet per second. And theta is the angle with the horizontal. Then we can model the flight using parametric equations. X equals v cosine theta times t, while y equals v sine theta times t minus 16t squared plus h. T is time in seconds. The negative 16t squared is a result of gravity's pull of gravity. Let's pull the ball back down. But x is going to give the horizontal position. Y is going to give the vertical position of the ball. And each one's going to be in relation to time t. And we're ignoring air resistance. If you have air resistance, that's another variable you got to put in there, but we're going to ignore it for now. Okay. So let's apply this to golf. Throw a ball, hit a ball, whatever. Flies up in the air, it's going to go in this arc. Let's say we hit 3 golf balls. So they're taken off from the ground. Oh, first too, don't forget, I forgot to tell you what H was. The H up there is the ball's initial height from ground. as I was thinking about golf balls. I remember, you're hitting the golf balls from the ground. So in the golf ball case, the h is going to be 0. But if you're a baseball player throwing the ball, you have a certain height from the ground that you're already starting the ball from. And then it's going to go through the air, and then it's going to hit the ground later. So you have to take that into account right here with this plus h. All right, we hit 3 golf balls. It's going to be our deal. It's going to be our situation. We're going to have velocity of 120 feet per second. One of them is going to be at an angle of 25 degrees, one's going to be hit at an angle of 45 degrees, and one's going to be hit at an angle of 65 degrees. And we're going to analyze what's happening here. We're going to figure out, assuming the ground is level, we're going to figure out which ball travels the greatest distance, and we're going to estimate that distance. And we're also going to figure out which ball goes the highest, and we're going to estimate that height. But we can use our flight model here to come up with some equations. And what we're going to do is we're going to put these equations into the calculator, and we'll compare the graphs in the calculator. Alright, so for the first ball, for ball 1, x sub 1 is going to equal 120 times the cosine of 25 degrees times t. Y sub 1 is going to equal 120 times the sine of 25 degrees times t minus 16t squared. We don't need the plus h because we're hitting them from the ground. H is for if it takes off above the ground somewhere. X sub 2 for ball 2, we're going to have 120, that 120 is at initial velocity, cosine of 45 degrees times t. Y sub 2 is 120 times the sine of 45 degrees times t minus 16t squared. So x will give you its horizontal distance, y will give you its vertical distance. X sub 3 is 120 times the cosine of 65 degrees times t. Y sub 3 is 120 times the sine of 65 degrees times t minus 16t squared. Okay, but this set of parametric equations will help us to model each golf ball that's being hit. First golf ball being hit at an angle of 25 degrees, velocity of 120 feet per second. Second, third golf balls all being hit the same velocity, but different angles. And we're going to put this in the calculator. And we're going to figure out what's going on here. So x sub 1, we're going to put, let me make sure I'm in degree mode because this problem's given the angles in degrees. I'm also parametric, so that's good. Alright, x sub 1, we're going to have 120 cosine of 25 times t. Y sub 1, we're going to have 120 times the sine of 25 times t minus 16 t squared. Okay, that's just for golf ball 1. Golf ball 2, we're going to have 120 times the cosine of 45 degrees t. And then we're going to have 120 and the sine of 45 degrees times t minus 16t squared. Then for the third one, third golf ball, we're going to have 120 cosine of 65 t, and then we're going to have 120 sine of 65 times t minus 16t squared. I'm just kind of glancing over them, trying to see, make sure they look right on here. Trying to double check, make sure I type things in correctly. So I'm just quiet. That's why I'm kind of not going to talk here. I'm just looking. Okay, as far as I can tell, I didn't make any mistakes typing them in. For our window, T-min, T-max. Let's see here. What do we want to use? How about, let's do T is 0 to 9. Just see what happens if we do that. And then let's do 0.05. Alright, then X-min is going to be 0. X-max, let's put it at 500. And let's vary by 50. Then Y-min, 0. Y-max, let's put 200. And we'll vary at 50. See what happens if I do that. Alright, so there was golf ball 1. Let's see what its path looks like. There's golf ball 2. And then there's golf ball 3. Okay, very interesting. They all hit the same velocity, so same initial speed. Golf ball 1 at the lower angle of 25 degrees stays low, lands here. Golf ball 2 at the higher angle of 45 degrees goes higher and actually goes further. Golf ball 3 at 65 degrees goes really high, but then drops down before golf ball 2 did. So it travels the highest but not the furthest. So golf ball 2 traveled the furthest, golf ball 3 traveled the highest. And the question's asking, also how far, how high. So we can use the trace feature on the calculator to help us to see what's going on these graphs. So if I just go left or right, it'll move the X on the same graph. If I go up or down, it'll jump it to another graph. So let's see here, trace. I'm up here. 164, 67, 169, 172, 174, 177, 180, 182, 185. Interesting. The Y, the height, let's see here, the height, you have 184.65, 184.77, 184.81, then all of a sudden it goes back to 184.77. So we can say that the height, the greatest height's around 185 feet. So at the 65 degree angle, we max out the height at around 185 feet. And then let's hop to another graph. Let's try to hop to the graph that, there we go, that goes the furthest. Let's trace it. Alright, right here, Y is at 0.27, then Y hops down to negative 0.3. The X is 453.9 or 449.7. So 0.27 is at 449. You can say about 450 feet is the greatest distance. And that was for golf ball 2. That was the one that was hit at 45 degrees. So we want the distance, you hit 45 degrees. If you want height, you go 65 degrees at 120 feet per second. But we just used the calculator to do that. We graphed them, and then we used the trace feature to let it tell us what the coordinates were, and we could get at least an approximation that way. All right, one more example. Let's do one more example. We got a toy rocket that's launched. And it's launched from the ground. It's got a velocity, initial velocity, at 36 feet per second. And a 45-degree angle with the ground. Alright, and it says find the rectangular equation that models this path. Alright, with parametric equations, we know that we can write x equals the initial velocity 36 times cosine of 45 degrees times t. Then we also can write y equals the 36 times sine of 45 degrees times t minus 16t squared. We don't need to add a plus h because this launched from the ground. Well, if we go through and take cosine of 45 degrees, we get what? Square root of 2 over 2. Multiply that by 36. We're going to get 18 square roots of 2 times t. On the other side, square root of 2 over 2 times 36 will give us 18 square roots of 2 times t minus 16t squared. Well, if we want a rectangular equation, what we can do is make a replacement, like solve for t here, and then replace in the y equation for t. That way we're getting rid of t and turning this from parametric into parametrics with t to rectangular with xy. So we got y equals x minus, if you do a little bit of math here, you're going to get 16 over 648 x squared. But you can reduce, so you get y equals x minus, the 8 will go in, so you get 2 over 81 x squared. Or you can say y equals negative 2 over 81 x squared plus x. And so we get a quadratic equation, which is going to be a parabola. And since this number here is negative, we know the parabola goes like this. Which makes sense. We're launching a toy rocket from the ground. It's taking off, it's going to peak, and then it's going to come back down to the ground like that. That's going to be the flight path of the toy rocket. Just like that. So that's where we're getting upside down parabola. Now we can go on and use that information to determine the total flight time and horizontal distance traveled. Well, if this rocket's taking off on the ground, going up, then coming back down. T is going that direction. Time is linear in our world, and it's going from left to right. Like here t is 0, here t is something. If we can figure out what this something is, That'll tell us the flight time. It'll tell us how long it took to go from point A to point B. Also, if we can figure out what x is here, that'll give us our horizontal distance. Alright, well let's do this. Let's take, if we want to figure out our x's, like we know our beginning x and our ending x, we can subtract them if necessary or whatever. And at these 2 points, the y is 0. So if we take our equation up there and substitute 0 for y, we can solve that quadratic equation and get the 2 x values for when the rocket's on the ground. So let's see here. We really got 2x squared minus 81x equals 0. Factor out an x. Just do a little factoring. You don't have to do quadratic equation or anything. You got x equals 0. And then if 2x minus 81 is 0, then x must be 81 over 2, which is also 40.5. Okay, so x equals 0 would be this point here. So apparently what we got with this rocket, alright, we got starting at 0, 0, makes sense. It launches, takes off, comes back down, and then it lands here at 40.5, 0. So it travels 40.5 feet. And how much time does it take to do that? Well, we know that t equals, if we go back up here, t equals x over 18 square roots of 2. So when it lands at 40.5 feet right there, we want to know what the t is at that point in time. So just put that in, divide, and you get roughly, if you go ahead and round, you get about 1.59. So about 1.59 seconds is all it took for that toy rocket to fly, do its flight. Not a very long flight, less than 2 seconds. But there you go. So now you can work. You could, if you wanted to too, you could go back and figure out the vertical distance, figure out where it peaked. You can get all kinds of information from this parabola. Not just x and y, but also time t. So that's where parametric equations are so great. If you end up taking any kind of physics classes, you're going to be using this stuff quite a bit. Alright, well, that's enough excitement with this for now. I do appreciate you joining us. So go on, have fun solving more parametric equations, and I'll see you again sometime. Thank you.